Thank you for joining us on the Blue Swan. Today we have Tal David and Amit Ben Kish, who are the founders of Quantum Art, which is a quantum computing startup that raised an $140 million Series A, the largest Series A financing in quantum computing, and was subsequently prematurely featured on the New York Stock Exchange, which is foreshadowing if I've ever seen it. And so, on that note, would you guys mind sort of discussing yourselves, your work, and anything you'd like to say?
Hi, Sean. Thanks for having us. So my name is Tal David. I'm the CEO and co-founder at Quantum Art, a quantum physicist with experience in academia, industry, and government. I was head of Israel's national quantum strategy, and 4 years ago embarked on a new path together with Amit and our third co-founder, Professor Roy Ozeri from the Weizmann Institute, who's not here on this call, to form Quantum Art and build the world's best quantum computers. Amit?
Thank you for having us. So my name is Amit Ben Kish. I'm also a physicist. I did my postdoc at NIST Boulder with Dave Wineland, who, as you probably know, won the Nobel Prize for quantum computing based on trapped ions. I did a long career in the industry, and 4 years ago we joined forces and to make quantum art happen. And I'm the CTO.
I'd like to just jump straight to quantum AI. And so, you guys have successfully formed partnerships with a number of large companies, some of which include NVIDIA. And so the nature of what quantum spins do like creates a completely different set of possibilities computationally when it comes down to either the discrete or probabilistic side of AI algorithms. And I'm wondering if you would be willing to sort of touch on how that changes the nature of AI computation and then also how it will evolve with it.
Yeah, so I'll start and Amit will go into the more technical details. So, AI is a real revolution. It's disruptive. But basically, it's a software revolution. It's based on the same CPUs and GPUs that we're running the AI applications on. Quantum is a whole different story. It's a paradigm shift. It's a new kind of logic, and it comes from the hardware first. So essentially, AI and quantum will complement each other, and anything that you can do on AI, you can implement now not on the CPU and GPU, but rather on the QPU, the quantum processing unit that is at the heart of quantum computers. So this has two main implications. The first one is, or I would say three implications. The first one is that quantum will accelerate some of the workloads that AI is doing. Okay, it could be optimization problems, or learning problems, or protein folding problems, and so on. And the speed ups that are expected when quantum will accelerate AI could be a factor of 1 million or more in some of these workloads. That's one. The other thing is that at the same time, the energy consumption of quantum computers is drastically less than what you find in AI data centers. And there are predictions that within the next 3, 4, 5 years, the difference between working in AI data centers as we know them today and how much power they consume, and working in a hybrid quantum and classical AI data center would be orders of magnitude. The energy consumption, benefits would be on the scale of the energy consumption of whole countries in just a few years' time. So that's a very, very big deal, especially when you think about AI data centers today, um, uh, starting to build nuclear power plants in order to supply the energy for them. So that's a real, real disruption. And then the third part is that AI is also helping quantum in the other way. We're using AI to design our quantum computers, to carry out very complex problems in quantum and so on. So it's a kind of a two-way street. Amit, you would like to add?
Yes, maybe I'll jump into some additional point regarding to our architecture. So we're working with trapped ions and we're working with multi-qubit gates. And as quantum computing is a universal set, in practice, you can do anything, including AI. So any type of computation you would be able to do on a classical computer, you can do on a quantum one, except the fact that you have like exponential memory, and you have like and you can do things much faster with much less energy. So what you would do, so there is a field of using AI on a classical computer, and the analog to this is called quantum machine learning. And what we're also doing is like trying to figure out algorithms at which quantum will enable getting to results much faster, easier, and sometimes wiser. So I think there is a revolution here which comes together. It's the hardware that we have, and together with the AI software that makes things much better.
There's been a ton of investment in everything from nuclear power to underwater data centers that are essentially being built, towards the bottom of the ocean. And so the computational cost and sort of the energy consumption related to it is a massive bottleneck. And so, with that in mind, how do you see quantum computing sort of moving more towards storage? There's essentially DNA-based data storage, and that at a fundamental level, it's an order of magnitude more efficient. The difference is that quantum computing it involves a different set of particles and thus sort of a very, very different scale. And so, is there a chance you could touch on that?
First, I think the the strength of quantum computing is the ability to calculate large amount of data. It's not the streaming of data, but the amount of the ability to calculate while using a large amount of information. So actually, the memory is built into the computation process. You start with a very small amount of qubits that enter the system. You get out not many so many qubits, but there is an exponential number or volume that you can actually address and can calculate. So basically you would reach direction that which you would not be able to address before. So for example, if you would like to calculate some chemical reaction, you won't rely necessarily on a large amount of data, but you would let the computer start from some sort of an initial state, calculate the process, and give you the result that usually you won't be able to get using classical means because you don't have the ability to either calculate fast enough or have the storage to have all the information. Whereas this information is already built into the process or the algorithm itself.
Let's give a quantitative example for what Amit just said. Let's say that you are a pharma company like AstraZeneca or Pfizer or any of these guys, and you want to develop a new drug, and you're looking at molecules having, let's say, only 300 atoms. That's a very small thing, right? In order to simulate that, you need to span a computational space which is huge because you have 300 atoms. How do they connect with each other? How do they relate to each other? You have many, many possibilities. Okay. Um, when you're encoding that into a quantum computer, each quantum bit or qubit, as Amit said, is holding part of that information, and the scaling is exponential, meaning that you can encode the whole computational space in just 300 quantum bits or qubits. And the computational space or the number of possibilities that you can compute in the quantum computer in parallel is 2 to the power of 300. Okay, that is a number which is larger than all of the particles in the universe. Okay, so the input and output from the quantum computer is just 300 bits. Okay, but the computational space that we calculate on is at the size of 2 to the power of 300. Okay, so it's very little in, very little out, but in between, we have extremely high complexity calculations being available using quantum computers. And no classical computer on Earth can even get close to that.
Thank you for clarifying that it's more a matter of the computational efficiency than it is the type of particle that the data is essentially being processed through. And so with that in mind, how do you eventually see the quantum computing branching out further into the hardware space because right now it's really limited more towards institutions and so the focus on drug discovery or algorithmic trading or radar for solving traffic issues, all of that is very very much done through institutional partnerships. And so how soon do you kind of see quantum chips being embedded in laptops or even smartphones down the line? And then how do you see some of the temperature issues being solved with that? Because the temperature for which the qubits need to run at is like absolute zero. And that's not the easiest thing to do when dealing with, laptops and cell phones.
Yeah, well, I'm not sure we'll see quantum computers in your iPhone anytime soon in the sense of the quantum hardware. What you will see is quantum computers being added to data centers and to cloud providers, and then you can access them through the cloud from your iPhone. And actually, you can already do that today with about 20 different vendors offering quantum computing services over the cloud, what we call quantum as a service. Okay. So I would not expect the actual hardware to be miniaturized and go into laptops anytime soon. It may happen in the farther future, I don't know, but not anytime soon. And if you want to ask where is the time that this will have the ChatGPT moment in the terms of the commercial viability, not so much in terms of consumer use, I would say that there are two important points in time. The farther out point in time is about mid next decade, where companies will get to a level of about 1 million qubits. Okay, right now we are at the level of a few tens or maybe 100 qubits in the systems that we have today from all of the industry partners and companies involved. So mid next decade we'll get to 1 million qubits, and that is considered the utility scale and unlocking the full potential of quantum. And you could see that target being defined by governments like a big DARPA project in the US, a similar project in the UK now, and so on. So that's one point in time. The other point in time is when are we going onto the playing field, so to speak? When is the initial point where quantum will start to show usefulness? We call that point quantum advantage. Okay, and quantum advantage, in order to get to that, you need to be in the order of a few tens or a few hundred logical qubits, which is a measure that can be achieved when you have a few thousand or a few tens of thousands of physical qubits. This, according to all of the roadmaps, including Quantum Art's roadmap, is expected to come at the next 1.5 or 2 years, end of 2027 or maybe early 2028. And that will be the first time that quantum will surpass classical computers, even the most high performance of them, in commercially interesting problems and not the boutique demonstrations that we're starting to see in the last few years. Okay, so these are 2 points in time.
Yeah, maybe I'll just start for a second on the cooling process that you've mentioned. So yeah, that could be a bottleneck, but it depends on the modality. So in some cases, you would like large dilution fridges. That what these are the pictures you usually see in the media, and I think it's related to superconducting qubits. It's not necessary in all modalities. For example, using atom or ions, you don't need to cool the whole system. The trick is instead of cooling the whole environment, you just cool the qubits themselves or the atoms or the ions that hold the information. So there is orders of magnitude of material size that you would need to cool. In our case, for example, Tal mentioned like thousands or so qubits. We need only to cool them. On the other hand, if you have to cool the whole fridge, it will need a lot of power in order to make that happen. So the trick here is based on Nobel Prizes that people got like 2 decades ago, is using optical power or lasers to cool particles into the ground state or almost to the absolute zero. So the trick is to use lasers, which are very efficient, also to cool the ions. That's one thing. The other thing, using ions in our case, as well as using atoms, the qubits themselves are perfect. God made them perfect. All of them are the same. there is you don't need to produce them. They are already made, and you just need to use them. The thing is that you need to, and there are, we used to call them that they are perfect qubits. We apply magnetic field, electric field, lasers, and all of these needs to be very stable in order to make the process happen. This can have some error, which is the error that is related to the physical qubits. In order to surpass this problem as well, what people do is they take a few qubits, say 10, 20, and they bunch them together, and they are used as a logical qubit in order to operate a system without errors. As long as you're fixing errors faster than you having errors, you can have an infinite circuit depth that will calculate anything that you would need. And there is also a difference between modalities. Whenever your fidelities are very good, this ratio between logical and physical is different. And for traptines, the ones that we're using, this is considered very relatively small, and we're talking about 10, 20, 30, depends on the specific code that you're using as a measure for getting logical qubits to be used as part of the process.
Yeah, I'd like maybe to add an explanation connecting that to the first point in time that I mentioned coming up in 2027 or 2028. Why do we need a few tens of logical qubits or a few or maybe 100 logical qubits to go on the playing field and start to be commercially viable? It is because it is starting to be considered as an agreed upon fact that when you get to that level, it means that you're surpassing whatever high performance computers can ever dream of doing. Okay. If you take an HPC, high performance computer, and you want it to emulate quantum computer, the computational power of the strongest classical computers out there is equivalent to about a quantum computer with 50 perfect qubits, okay, noiseless qubits. If I have a quantum computer with 50 perfect qubits and I add just one more, we said the scaling is exponential, right? So we're now doubling the power related to the strongest high performance computer in the world. If we're adding another qubit, now I have 52, I'm now 4 times as powerful as the quantum computer, as the classical computer can ever be. Okay, so it's really a dramatic thing. Now, what's the caveat here? The problem is that our qubits are not perfect qubits. Okay, they have noise, as Amit said. We're taking a bunch of them and encoding them like an effective qubit that has lower noise, such that the threshold to do correction of mistakes on the fly is beneficial and not harmful. And so once you have a few tens of logical qubits, let's say up to 100 logical qubits, it means this is the point where we're surpassing the most powerful quantum classical computers out there in the world, and this is considered to be the beginning of commercial viability, or what we call quantum advantage.
It's interesting to kind of see the latency between academic discovery and commercial development. And so, for instance, Hopfield networks were discovered 50 or so years ago, but the Turing Award and the Nobel Prize in Physics weren't awarded for them until, just a few years ago. And so a lot of that is not functionality or whether something can exist. As part of it is just the economics of scale, which quantum computing is just blowing away. And on that note, sort of how do you see it branching out further into the hardware space? And because there's a little bit of a dichotomy between something sort of less visible, such as data processing through quantum processors versus an actual in an output being rendered, such as a visual production on film or maybe some sort of a hologram. And so, how do you see that gradually evolving over time, since much of this is based on the physics of waves and what human beings actually experience at a fundamental level in entertainment is as light and sound being rendered and then experienced.
Right. So that's a very interesting question, and I think the answer is cool and a little bit surprising. Um, there are not that many applications that have foolproof that quantum computers will bring tremendous impact in. but each of them opens up a world of opportunities. So, for example, we just announced recently work that we did with a customer on solving the wave equation using quantum computers. And we've shown that we can, in principle, surpass the strongest high performance computers in problems that they cannot solve, and we can solve at the level of 100 logical qubits or so. Okay, so it's getting to be closer because the level of 100 qubits will be there in 1, 2 years' time. So the idea there was to take a vast area where you have, let's say, a few cell towers radiating electromagnetic waves. And we wanted to analyze what would be the profile of this wave propagation in realistic scenarios where we have reflections from topography or buildings, and you may have other signals interfering with you, and so on and so forth. So this is an application in communication technologies, right? But then mapping out that problem into visualizations in art, for example, it's the same type of equations that look at how wave-like entities propagate. Okay, so if you would like to simulate waves in the ocean in computer animation in a very detailed way with extreme precision, much better than what you have today. This is the same type of problem, and you can map out one application and use the same approach in another similar application. So in a similar way, we can do a lot of mapping between different problems and take, for example, problems from, fraud detection in financials and map that problem into, let's do precise image processing and classification in images and so on. So that's pretty cool that you can migrate these ideas from one field to another.
How much of this is largely a result of hardware optimization, and then what kind of variance may or may not exist depending on these software applications that are run on quantum computers? Because the kinds of computations that are done on anything from protein folding to algorithmic trading or even fraud detection, there's a very, very different set of mathematical objectives that are being looked at in variance within, points in time, and then the degree to which that is important.
So maybe I'll address the process and then we can take some examples. So first, as we mentioned before, a quantum computer is a universal computer, meaning that you can effectively do any computation you would like to, calculate on your classical computer and more on a quantum one. And the process goes the following way. First, a customer, a scientist is interested in solving a problem. Then he usually formulates this into mathematical tools, and a mathematical algorithm that needs to be solved. What's nice now with the current status of quantum computers that we've set a language called a circuit that you can type the circuit in your own computer and send it to a data center or a quantum computer, and this circuit is there is a formula for these circuits. It's a full set that you can use for any algorithm. You just need to type your algorithm and then to process it through the pipeline towards the system. In our case, what we've done is we're using the hardware, in our case, trapped ions, as well as multi-qubit gates and reconfigurable cores, in order to make this calculation very efficient. So the next steps under the hood, in our case, we take this circuit, we massively compress it with software tools called compilers, transpilers. We take this information to the language that is used on the machine, let the machine calculate this, and then send it back to the person that sent the job in order to get the result. So the process is in the prospect of the end user is similar to using a software on his computer, but under the hood there is a quantum computer that actually does the thing. And referring to your question, what we have done is we've develop a unique architecture that can go a long way in terms of the scale up, as well as another layer of software that compress or takes the most out of the QPU, the quantum processing unit, to make the process as efficient as possible, and in some cases orders of magnitude better than what you would get from other modalities.
While the quantum computer is a universal platform and it can calculate any algorithm that you want in principle, on the path to there, where quantum computers are in the process of scaling up until we have unlocked the full potential of the technology, you have different approaches or different qubit technologies. We're working with trapped ions. Other people are working with atoms or with superconducting qubits or other qubit modalities in our jargon. And on the path to there, some of them will have advantages or shortcomings for different types of calculations. So for example, in superconducting qubits, the operations are super fast. Okay, so if you want to do something that is less accurate or less high quality performance, but it requires to be very, very fast, we'll probably go to that modality first and not to atoms or ions, which excel in performance, but are typically slower. In quantum arts architecture, we're bridging the gap. We're taking the best of several worlds, several advantages of different approaches, and bringing them together. So we're using the high performance, the connectivity, and the stability of trapped ions, but also the scaling and parallelism and reconfigurability of, let's say, neutral atoms in order to bridge the gap and do both high performance and also fast operation. And because of this, we can not only go the distance to extremely large number of qubits, but we can also shorten the path and do more with less resources, meaning that we can get faster into a commercially interesting and meaningful application solving.
Science aside, raising that amount within a period of about 4.5 years is a massive change. And so I wonder if you would be able to touch on sort of the stages from inception to where we're at now post Series A, because that involves a massive change in an employee base and everything from financial reporting to the actual infrastructure you need to operate and and corporate governance as well.
There's a long way to go, and there's much more money to raise. So Quantum Art was spun out of the Weizmann Institute from the group of our co-founder and chief science officer, Professor Roy Ozeri, in 2022. All of the three co-founders, we go back many, many years in academia, industry, and government. And so it was natural for us to join forces and set up this company. And the starting point was that Roy at Weizmann has uh, built the first full stack quantum computer in Israel in any qubit technology with state-of-the-art performance of a few qubits, a small quantum computer. And we understood at that point that this is the right time to go ahead and take it beyond what academia can do in the commercial sense. Okay, so we joined forces in 2022. We raised our seed round, which was $24 million by four Israeli venture capital firms, and we got started. I think the most important thing is the people and the team. We have brought one of the best teams on the planet, people coming from the best institutions in research like Harvard and Stanford, and in Israel, Max Planck in Germany, and in Israel, it's Weizmann and Technion and Hebrew University. And also we brought excellent people from industry, both local and multinational, like from Applied Materials and KLA and Intel and so on and so forth, and Google now. So everything starts and ends with the people. Right now, we are a team of over 60 people working very hard on all aspects of quantum computing, the hardware, the software, the applications, and we got started to work. Okay. Um, to that, we added non-dilutive funding from paying customers, from governmental grants and projects, both in Israel and abroad. And very recently, we have closed our Series A round, as you said at the opening statement, at $140 million approximately, which is the largest ever Series A round in quantum. Why do we need that? We need that because this is damn hard tech. Okay, we're using very vast multidisciplinary systems that have to do with quantum physics and lasers and electromagnetics and optics and vacuum and software. And all of this needs to play together, and it's a very hard effort in order to bring this at the utmost performance. Amit said that we're working with atoms and they're perfect qubits, okay, or ions in our case. We just need not to interfere with them. So, not to interfere with them and to bring out the most of them is a very, very challenging engineering and even scientific in some senses. So we need a lot of capital to bring in the best people around to build the best hardware and to bring this to market, right? Because we need to have this serving customers and working together with customers to identify what this can bring to them and educate the market and create the community of users to adopt the technology and go with it. So there's a lot of things to do. We have a very full plate, and for that we need capital. I would say, and maybe I would ask Amit to elaborate on that, that between the different qubit modalities, the capital intensity is very different, right? For example, in terms of fabrication.
So in terms of fabrication, I think we are fabless. Both neutral atoms and ions do not need fabs at all. So that's, in terms of capital that you would need, we just get the ions or the atoms. In our case, we've started with the best qubits we know of. It's trapped ions. Both Roy and I worked at the Wineland group and other groups, and then I think that everybody knows that the best performance you would get on the planet or you would get from trapped ions. Then the question would be, how would you scale this up into a large system? We're aiming towards 1 million qubits in a 2-inch by 2-inch footprint, which is very, very small. You have imagined like a very big system with a lot of cooling capacity, but in our case, it's not the case because we are using lasers, focused tight beam lasers, in order to make the operations. And we've came up, as Tal mentioned, with a new and novel architecture to take us through this trip. And I think it incorporates few steps that I think they are new to the industry. They were taken from ideas both from the modalities of trapped ions as well as atoms, and we joined things together to make the most powerful expected computer based on few steps that we're doing. And this includes what we've, so usually all the industry is using a full set based on single and 2 qubit gates. What we do, we called it multi-qubit gate. These multi-qubit gates are beasts, are able to make a lot of calculation in one go. Just for example, if you feel just 50 qubits, you would be able to do 1,000 operations in one step. So in one step of multi-qubit gate, we're able to compress thousands of layers of regular quantum computers code. So this makes it much faster as well as more efficient. The other things that we do, we work with multi-cores, not one core, but many cores. But everything is done on just a small string of ions, which is millimeter size. So each core is a quarter of a millimeter, and if you have like 1,000 cores, it's a few millimeters, not more than that. So 1,000 qubits is about few millimeters. It's very small, and that goes towards million as well. And the last thing in terms of the architecture, it's reconfigurable. We called it, it's similar to what we would say about it, like with your FPGA, you can use software to reconfigure your hardware. We called it like a quantum FPGA, at which we can reconfigure the cores and connect them in a quantum way, meaning that we can get to very powerful results while using a very tiny and small system. So first we rely on the best qubits called trapped ions, and then we have a unique strategy towards scale up that will take us all the way to these quantum advantage and further towards like the commercial viability of these systems.
That really is incredible at a computational sense. It's a brief last question. And would you be able to touch on how studying with a Nobel laureate provided some of the foundation for developing this years down the line?
I had the privilege to work with Dave Wineland at Nest Boulder 25 years ago. I think Dave is one of the nicest person I ever met and one of the cleverest ones that I've met. So he's great, and I think many a lot of the companies that span out of this hub actually initiated companies like people are coming from many companies that you know of, like Continuum and IonQ, actually were, and some of the startups at Europe actually were, these are Dave Wineland students, and it was a very nice and impressive uh, part of my academic life, learning to work with such a talented guy. And he's very modest and he knows a lot. And so, and when we came there, he already wrote a paper. It was like 200 pages. We called it the book, the Bible, sorry. And the Bible were actually, he just sort of sorted out what would be the processes for the next 20 years of making quantum computers. So this Bible was very important to all, the postdocs that came there. And then each one of us took another approach. We took some different approach from the usual approach taken there on using quantum CCD, and we're using other ideas that were actually built later on based on optics and tweezers to take the next steps.
I think that the main message that is important to send out to the general purpose audience is that quantum is no longer a science fiction thing of the far future. It's already here. It's approaching real usefulness in the next 1, 2 years, right? It's within sight. On the other hand, this is not like taking a few CPUs and GPUs and putting them together to build a machine. This is a whole different philosophy. It's a paradigm shift. And in order to be prepared for that and not miss the train, people need to start understanding what this could bring as benefit for them today. And today, most of the Fortune 500 companies are already testing the temperature of these waters and trying to do application development and understand what will be the added value and when this will come to them. And so, my recommendation for people out there is understand what this is, what it can bring to humanity, how it will change people's lives on the planet. And if you are in a technological organization, just go ahead and get your hands dirty. Start to use the quantum simulators, the quantum computers, in order to understand and be prepared to unlock this amazing revolution in the very near future.
Thank you so much for doing this. This was really fascinating.
Thanks
So
for having us.
Thanks a lot.